Good morning to one and all. I'm Dr. Gejalakshmi, Professor, Head of the Department, Pharmaceutical Analysis Department, Faculty of Pharmacy, Dr. MGR Education and Research Institute, going to present you a topic on gas chromatography. Before entering into gas chromatography, let me explain about what is chromatography. It is a physical method of separation. No reaction occurs during the separation process. The components partition between two phases. One is said to be the stationary phase, the other is said to be the mobile phase, which moves along the column. The separation of the solute occurs owing to their volatility, the different interactions within the two phases. History of the chromatography. Russian scientist Mikhail Semenovich Svet is credited for the discovery of chromatography in the year 1903. In 1947, German student Fritz Preyer is credited for developing gas chromatography. Gas chromatography, modern gas chromatography, John Barton Martin is the father. He developed the first liquid gas chromatography instrument in the year 1950. He won the Nobel Prize for Chemistry in the year 1952. Gas chromatography principle. Sample is injected to a vaporized onto the head of the chromatographic column. Elution is produced by the flow of inertial gaseous mobile phase. Mobile phase used for the gas chromatography is usually gaseous state. Separation is based upon the partition of the vaporized analyte between a gaseous mobile phase and a liquid phase immobilized on the surface of an inert solid gas liquid chromatography. Inert carrier gas does not interact with the molecules of the analyte. Eluted analytes are detected by a detector and recorded by the data system. GC column or gas chromatography column are either particles are coated with liquid stationary phase or capillary, the most used now, which is frequently used analytical advanced technique for nowadays. Chromatographic separation process flowchart has been given here. Injection is done through the inert carrier gas and the detector are detected. Then the sample limit passed through the column at 0 minute, 5 minute, 10 minute intervals. Least increasing solute volatility leads to increased most, whereas the interaction with stationary phase will take more time to elute. The sample which are more interaction with the mobile phase are eluted faster, and the sample which has more interaction towards the column stationary phase are a little slower. The theory of the chromatographic principle depends upon the typical chromatogram, where taking the time along the x-axis and detector signal along the y-axis. The injection time and the time taken for the molecules to flow through them are noted through the elution time, where T R represent the retention time, Tm void time or dead time, Wb the baseline width of the peak, Wh the half height width of the peak. What is cause for the peak width? Each elution band spreads due to the several phenomena. The main cause for the peak width are eddy diffusion, mobile phase mass transfer, stagnant mobile phase mass transfer, stationary phase mass transfer, and longitudinal diffusion. Eddy diffusion, the process that leads peak broadening due to the presence of multiple flow paths through the packed column. So the solute 1 longer path, higher retention time, whereas the solute 2 lower path, that is lower retention time, the shorter peak. In a capillary column, there is no packing, there is no eddy diffusion. Then peaks are narrow and separation takes place. Chromatographic peak. Supposed a Gaussian sigma standard deviation, delta width at height, half height, omega baseline width. Since it's often difficult to accurately evaluate the equation, use the width at height and delta, which can be easily measured on the chromatogram. Same fundamental equations are used for the corrected retention time, where TR equals to TR minus TM, where the capacity ratio corresponds to the relative retention K equals to TR divided by TM, which is nothing but the difference between the TR minus TM divided by the TM. Column selectivity alpha equals to TR2 divided by TR1, which is equals to K2 divided by K1, where alpha greater than 1 because TR2 is greater than TR1. Resolution between the two neighboring peaks occurs where it is the summation of TR2 minus TR1 difference divided by the summation of omega 2 plus omega 1. For two neighboring peaks, a resolution RS higher than 1 means a complete separation. RS equals to 1, the overlapping peak surface is 2%. Where RS is less than 0.8, the separation between the two peaks is considered to be incomplete, which is nothing but the fundamental equation involved in the gas chromatographic separation. Column efficiency depends upon the Gaussian principle. The peak broadening can be related to the separation and column efficiency, which is evaluated by the number of theoretical plates of the column, similar to the distillation process for a Gaussian peak. N can be calculated by one of the equation where N equals to TR divided by sigma whole square, where sigma represents the standard deviation of the peak. N equals to 16 divided by omega square, where the omega represents the width of the baseline. N equals to 5.54 TR divided by delta whole square with that half height. In order to compare the columns having different length, one calculate the height equivalent to the length of the theoretical plate. H equals to L by N, where L represents the column length. H may vary from centimeters packed column to several microns, which is nothing but high resolution capillary column. Gas chromatography equipments. Main parts of the gas chromatography are, it consists of a gaseous carrier gas, which may be hydrogen, helium, or nitrogen, injector, column, oven to maintain the temperature, FID, which is nothing but a fluid ionized detector, and the data processing unit. The carrier gas should be inert. The best carrier gas used for the study is helium and nitrogen. Hydrogen is highly flammable, so it is not recommended for the study. Gas supply, compressed gas cylinder, double stage pressure regulator, valve, gas filter to eliminate the impurities such as water, oxygen, hydrocarbon, other atmospheric air impurities. Then the injector port, it consists of the following parts like septum, carrier gas inlet, injector heater, liner tube, column inlet fitting. Column in gas chromatography, there are two types of column as in gas chromatography. One is said to be the packed column, the other is said to be the closed column. Packed column, usually the diameter or the internal diameter is 2 to 4 millimeter and 1 to 4 meter in long. Packed with a suitable adsorbent, mostly used for gas analysis. Peak broadening due to zone diffusion resulting from the multiple of pathways a molecule can pass through the column. 100 millimeter to 500 millimeter internal diameter and 10 millimeter to 100 meter long in a capillary column. Stationary phase is usually coated on the internal wall of the column as a film of 0.2 millimeter to 1 millimeter thickness. Sharper peaks, there is no eddy diffusion occurs. Most popular type of this particular column is used everywhere. Isothermal programmed temperature in the gas chromatography. Examples for gas chromatography separation are N-alkanes. Temperature gradient improves resolution while also decreases the retention time. Programmed temperature from 50 degrees Celsius to 250 degrees Celsius at 8 degree per minute. Isothermal conditions are 150 degrees Celsius. Taking time along the x-axis and detector along the y-axis, injection of the sample takes place from each column, where C1, C2, C3, 4, C up to C18, it has been recommended, and the temperature control mission was around 150 degrees Celsius. A typical temperature program in gas column are initial temperature and time, temperature ramp, which is measured in degree per minute, and final temperature and time. Temperature program can be more component. Characteristics of the gas chromatography detector. The detector should have the following characteristic like stability, reproducibility, specific detector, destructive, linear response to the analyte, temperature ranging between room temperature that is 24 degrees Celsius to 400 degrees Celsius, response time short and independent of flow rate, high reliability and ease of use. Flame ionization detector is the most popular detector among all the detectors used in gas chromatography. It is the most used detector in GC. Most of the organic compounds like pyrrolase in hydrogen air flame and produce ions and electrons. A potential of a few hundred volts is applied across the burner jet, and a collector electrode is located above the ion jet. The setting of the flame ionization detector results in collector electrode, insulator, collector nut, air, and inside oven wall, hydrogen air film, grounded jet, exit column. The resulting current is amplified and proportional to the number of carbon atoms in the flame. General detector for the gas chromatography, heteroatoms containing group yields few electrons, also intensive to water, carbon dioxide, sulfur dioxide, nitrous oxide. Larger linear response up to 10 to the power of 7 and low noise can be exhibited. It exhibits very high sensitivity up to 10 to the power of minus 13 G per S of the analyte per second has been observed. certain advantages and disadvantages of the gas chromatography. Fast analysis, typical minutes, high resolution, the plate number can be higher than 10. Sensitive detectors, easy ppm, parts per million, offer ppb or less. Highly accurate quantification, 1 to 5% RSD. Automated system, non-destructive detectors allow online coupling to the mass spectrophotometry. Small samples like microliter, reliable and relatively simple, low cost, that is around 20,000. The limited to volatile samples, temperature limited to 380 degrees Celsius. Above temperatures are not recommended for the gas chromatography. It needs vaporization around 60 tar at that particular 380 degrees Celsius recommended. Not suitable for thermally liable samples. Some samples may require extensive preparation. Derivatization process is required, which is not able to capable through the normal temperature. We need to undergo derivatization. Require spectroscopy, usually mass spectroscopy to confirm the peak identity